Dobry den, and welcome to the first part of our Unit 6 presentation on the normalization of database tables for CIS 3107 database modeling. We will be covering sections 6.1 through 6.3 in our text. In this first presentation, we will learn about what normalization is and what role it plays in the database design process, the normal forms 1NF, 2NF, and 3NF, and how normal forms can be transformed from lower normal forms to higher normal forms. The table is the basic building block of database design. Consequently, the table structure is of great interest, but how do you recognize a poor table structure, and how do you produce a good table? The answer to both questions involves normalization. Normalization is a process for evaluating and correcting table structures to minimize data redundancies, thereby reducing the likelihood of data anomalies. The normalization process involves assigning attributes to tables based on the concept of determination we learned in our Unit 3. Normalization works through a series of stages called normal forms. The first three stages are described as the first normal form, 1NF, the second normal form, 2NF, and the third normal form, 3NF. From a structural point of view, 2NF is better than 1NF, and 3NF is better than 2NF. For most purposes in business database design, 3NF is as high as you need to go in the normalization process. However, you will discover that properly designed 3NF structures also meet the requirements of fourth normal form, 4NF. Generally, the higher the normal form, the more relational join operations you need to produce as a specified output, and more resources are required by the database system to respond to end-user queries. A successful design must also consider end-user demand for fast performance. Therefore, we will occasionally need to denormalize some portions of a database design to meet performance requirements. Denormalization produces a lower normal form, that is, a 3NF will be converted to a 2NF through denormalization. However, the trade-off you pay for increased performance through denormalization is greater data redundancy. Database designers commonly use normalization in two situations. The first is when designing a new database structured based on the business requirements of the end users. The database designer will construct a data model. After the initial design is complete, the designer can use normalization to analyze the relationships among the attributes within each entity and determine if the structure can be improved through normalization. The second situation is when the designers are asked to modify existing data structures that can be in the form of flat files, spreadsheets, or older database structures. Again, by analyzing relationships among the attributes or fields in the data structure, the database designer can use the normalization process to improve the existing data structure and create an appropriate data design. The object of normalization is to ensure that each table conforms to the concept of well-formed relations and tend to have the following characteristics. Each table represents a single subject. No data item will be unnecessarily stored in more than one table. All non-prime attributes in a table are dependent on the primary key, and finally, each table is void of insertion, update, and deletion anomalies. From the data modeler's point of view, the object of normalization is to ensure that all tables are at least in third normal form. Even though higher level normal forms exist, they are not likely to be encountered in business environment. Typically, the normalization process works on one relation at a time and starts by identifying the dependencies of a relation table and progressively breaking the relation into new set of relations. Before outlining the normalization process, it's a good idea for us to review the Unit 3 concepts of determination and functional dependency that are used to derive the set of functional dependencies for a given relation. In functional dependency, the attribute B is fully functionally dependent on attribute A if each value of A determines one and only one value of B. Attribute A determines attribute B in the generalized definition if all of the rows in the table that agree in value for attribute A also agree in value for attribute B. Fully functional dependencies requires that if an attribute B is fully functionally dependent on a composite key A, but not on any subset of that composite key, the attribute B is fully functionally dependent on A. Two types of functional dependencies that are of special interest in normalization are partial dependencies and transitive dependencies. A partial dependency exists when there is a functional dependence in which the determinant is only part of the primary key, and we assume that there is only one candidate key. Partial dependencies tend to be straightforward and easy to identify. A transitive dependency exists when there are functional dependencies such as x to y and y to z, and x is the primary key. In that case, the dependency x to z is a transitive dependency because x determines the value of z via y. Unlike partial dependencies, transitive dependencies are more difficult to identify among a set of data. Fortunately, there is an effective way to identify transitive dependencies. They occur only when a functional dependency exists among non-prime attributes. The most common normal forms and their basic characteristics are listed here in Table 6.2. First normal form, 1NF, is a table format, no repeating groups, and PK identified. Second normal form, 2NF, is in 1NF with no partial dependencies. Third normal form, 3NF, is in 2NF with no transitive dependencies. Boyce Codd normal form, BCNF, is a special case of 3NF where every determinant is a candidate key. Fourth normal form, 4NF, is a 3NF with no independent multi-valued dependencies. As we progress through Unit 6 presentations, we will learn more details of these normal forms and how the normalization process takes you through the steps that lead to successively higher normal forms. In our conversion to first normal form, we will remove repeating groups. A repeating group derives its name from the fact that a group of multiple entries of the same type can exist for any single key attribute occurrence. The existence of repeating groups provides evidence the presence of data redundancies. Normalizing the table structure will reduce the data redundancies. Normalization starts with a simple three-step procedure. Step 1, eliminate the repeating groups. Step 2, identify the primary key. And step 3, identify all dependencies. An example of step 1, eliminate the repeating groups. We start by presenting the data in a tabular format, where each cell has a single value and there are no repeating groups. To eliminate the repeating groups, we eliminate the nulls by making sure that each repeating group attribute contains an appropriate data value. That change converts the table in Figure 6.1 to 1NF in Figure 6.2. Step 2. Identify the primary key. The layout in Figure 6.2 represents more than a mere cosmetic change. Even a casual observer will note that the proj_num is not an adequate primary key because the project number does not uniquely identify all the remaining entity row attributes. For example, the project num value of 15 can identify any of the 5 employees. The conversion to first normal form 1NF describes a tabular format in which all key attributes are defined. There are no repeating groups in the table, and all attributes are dependent on the primary key. To be in 1NF, all relational tables satisfy 1NF requirements. Some tables contain partial dependencies which are subject to data redundancies and various anomalies. Dependency diagrams depict all dependencies found within a given table structure. They are very helpful in getting a bird's eye view of all the relationships among a table's attributes, and their use makes it less likely that you will overlook an important dependency. In step 3 of our 1NF conversion, identify all dependencies, the identification of the PK in step 2 means that we have identified the following dependency. Project num and employee num have the dependencies of project name, employee name, job class, change hour, and hours. That is, the values are all dependent on and determined by the combination of project num and employee num. There are additional dependencies, such as the partial dependencies of project num, which has the dependencies of project name and employee num, and dependencies of employee name and job class and change hour, as well as one transitive dependency of job class dependent upon the change hour. Since this dependency exists between two non-prime attributes, therefore, It is a signal of a transitive dependency. These are depicted with the help of the dependency diagram in Figure 6.3, which shows all dependencies found within a given table structure. As you examine Figure 6.3, note that the following features of a dependency diagram. 1. The primary key attributes are bold, underlined, and in a different color. 2. The arrows above the attributes indicate all desirable dependencies. 3. The arrows below the dependency diagram indicate less desirable dependencies, which are partial and transitive dependencies. Conversion to 2NF occurs only when the 1NF has a composite primary key. If the 1NF has a single attribute primary key, then the table is automatically in 2NF. The 1NF to 2NF conversion is simple. Starting with the 1NF format displayed in Figure 6.3, you take the following steps. Step 1. Make new tables to eliminate partial dependencies. Step 2. Reassign corresponding dependent attributes. An example of Step 1, make new tables to eliminate partial dependencies. We look for a component of the primary key that acts as a determinant in the partial dependency. To create a new table with a copy of that component as the primary key. To construct the revised dependency diagram, we will write each key component on a separate line and then write the original composite key on the last line. With Step 2, reassign corresponding dependent attributes, we use the previous dependency diagram, Figure 6.3, to determine attributes that are dependent in the partial dependencies. The dependencies for the original key components are found by examining the arrows below the dependency diagram. The results of Step 1 and 2 are displayed here in Figure 6.4. At this point, most of the anomalies discussed earlier have been eliminated, because a partial dependency can exist only when a table's primary key is composed of several attributes. A table whose primary key consists of a single attribute is automatically in 2NF once it is in 1NF. A table is in third normal form, 3NF, when it is in 2NF and contains no transitive dependencies. Data anomalies created by the database organization are easily eliminated by completing the following 2 steps. Step 1, make new tables to eliminate transitive dependencies. And Step 2, reassign corresponding dependent attributes. A determinant is any attribute whose value determines other values within a row. If you have 3 different transitive dependencies, you will have 3 different determinants. As with conversion to 2NF, it is important that the determinant remain in the original table to serve as a foreign key. For Step 1, we use the 2NF in Figure 6.4 to identify one transitive dependency shown as its determinant, job class, to become the primary key in a new table, job. Thus, our transitive dependency is eliminated. Step 2 has us reassign the corresponding dependent attributes, change hour, to the new table, job, with their determinants and remove them from their original table, employee. In summary, normalization is a technique used to design tables in which data redundancies are minimized. The first 3 normal forms, 1NF, 2NF, and 3NF, are the most common. From a structural point of view, higher normal forms are better than lower normal forms because higher normal forms yield relatively fewer data redundancies in the database. Almost all business designs use 3NF as their ideal normal form. A special, more restricted 3NF, known as Boyd's God, defined all remaining attributes are dependent on the primary keys. However, a table in 1NF can still contain both partial and transitive dependencies. A partial dependency is one in which an attribute is fully dependent on only a part of a multi-attribute primary key. Furthermore, a transitive dependency is one in which an attribute is functionally dependent on another non-key attribute. A table with a single attribute primary key cannot exhibit partial dependencies. A table is in 2NF when it is in 1NF and contains no partial dependencies. Therefore, a 1NF table is automatically in 2NF when its primary key is based on only a single attribute. A table in 2NF may still contain transitive dependencies. A table is in 3NF when it is in 2NF and contains no transitive dependencies. And finally, a table that is not in 3NF may be split into new tables until all the tables meet the 3NF requirements. Thank you for viewing our Unit 6 Part 1 presentation. The diagrams and content of this lecture were derived from our textbook. For more detailed treatment of these concepts, please review pages 201 to 215 in our text.